Recording. Welcome to CPS. I hope you've all had a good week. Just before we start, if you would like to use closed captions, you can click them on the bottom of the screen. Today I have the honour of introducing Professor Omar Yaghi, who is currently the James and Nellie Tretter Professor of Chemistry at the University of California, Berkeley. He started off his career with an undergraduate degree at the State University of New York at Albany. He received his PhD from the University of Illinois and was an NSF postdoctoral fellow at Harvard. He is the founding director of the Berkeley Global Institute, whose mission is to build centers for research in developing countries and to provide opportunities for young scholars to develop and learn. He is also the co-founder of the Kavli Energy Nanosciences Institute, focusing on the basic science of energy transformation at the molecular level, as well as the California Research Alliance by BASF, supporting joint academia industry innovations. He's published over 300 articles and is listed among the most highly cited chemists worldwide. Professor Omar Yaghi is an elected member of the National Academy of Sciences and has been honored with many awards for his scientific accomplishments. I will try to highlight just a few since there have been so many. The Materials Research Society Medal in 2007, the American Chemical Society Award in the Chemistry of Materials in 2009, the Royal Society of Chemistry Spears Memorial Award in 2017, the Albert Einstein World Award of 2017, the Wolf Prize in Chemistry in 2018, a prize from the German Chemical Society in 2020, and most recently, the Sustainable Water Award from the Royal Society of Chemistry for the impact development of water harvesting from desert air using metal organic frameworks, which he's here to talk to us about today. Without further ado, I'll hand over.
Thank you so much, Kiera. And I want to also thank the other members of the CPS committee, Tina, Maria, Miranda, Sarah, and Blake. And I hope I'm not missing anybody else for organizing this talk and for doing a really wonderful job at putting this together. I would say, very impressive series. Today, I want to share with you some of our work in water harvesting from desert air. But since this application uses materials that resulted from reticular chemistry, I had roughly split my talk in half between sharing with you an overview of reticular chemistry, its origins, and how it works, and then dive right into the idea of harvesting water from desert air and some of the results that we have achieved so far. Since this is a student-based talk, I would say, let's ask this question: what are the most important materials today? And I think each one of you, after quick thinking about this question, will come up with at least half a dozen. And I'm pretty sure most of you will agree with me when I say, for example, wood, concrete, metals, glass, silicon, petroleum, plastics, pharmaceuticals, fabric, and paper. And these are, without doubt, materials that have, ecosystems have developed around them, and they have transformed our society. However, the future looks like we need to create materials that address energy problems, environmental problems. The problems of the future, or the problems of even the present, require new materials, require new type of control over matter, so that we can make materials that address today's problems and hopefully future problems. And the problems are quite, I would say, they're vexing problems in society. Being able to use clean fuels, storing and producing hydrogen for and using it for transportation and other uses. It's a clean fuel, produces as a byproduct only water, Carbon dioxide is another problem. Let's say a newborn today breathes double the amount of carbon dioxide than a newborn before the Industrial Revolution. So we have a lot of carbon dioxide into the atmosphere, and we're emitting a lot as well. So trapping this carbon dioxide from air, trapping it from power plant flue gas is a major problem that we need to address. And then water harvesting, or water access to water, clean water. 1/3 of the world does not have access to clean water today, even more. Whether they are living in desert regions or in watered regions, still there is a water stress in global water stress that we must address. These problems require us to control matter on the atomic and molecular level. It requires a generation of new kind of materials that could be utilized to address these problems. And of course, some of you who know me have already guessed what these materials are. They are really a result of a new kind of chemistry we call reticular chemistry. And reticular chemistry is defined as the chemistry of linking molecular building units by strong bonds to make crystalline extended structures. This definition has three very important contributions to materials. One is we're using molecular building blocks. So potentially one can design materials. Second, strong bonds, so that these building blocks are stitched together through strong bonds that to produce materials that are robust, so that if you're using them for carbon capture, as we do, they can stay in the power plant for many months, many years, without having to regenerate them or without breaking down. And third is the crystalline extended structures. We want to make crystals because we would be able to then analyze them with definitiveness at the atomic and molecular level, so that we know what we're doing. So these three things are new, I would say, concepts in terms of the making materials, is that we want to be able to put molecular building units together using strong bonds and to make well-defined materials. That has been a challenge in chemistry. And the result of this effort has been metal organic frameworks, and there is the yellow ball that Professor Paul Macmillan and I were lamenting on, is indicating the space within which gases and molecules and chemistry can take place, and control of matter can take beyond just what we can do, can be done. And also covalent organic frameworks. These are entirely organic structures that are linked by covalent bonds. We made the very first ones in 2005. These were 2D COFs, and then the 3D COFs in 2007. And now this is a big field in chemistry. And more recently, in 2016, we showed how you can take molecular threads and make molecular weaving. We were the first to show how covalent organic threads can be woven or interlaced with other threads to make extended structures. And this, again, this is becoming a fascinating field, because the mechanical properties you could make from these materials are superior to the mechanical properties that other materials that are not woven have. So perhaps in future I can come back and tell you about COFs and molecular weaving, but today I want to focus on MOFs as an example of reticular chemistry and their application to water harvesting. Well, as it says in the Bible, there's nothing new under the sun. So where did these metal organic or coordination networks, or so-called coordination polymers, started? They started in 1959. But what were they? They were made from copper ions linked by things like adiponitrile. This is a neutral linker that is makes a copper nitrile linkage, okay, throughout the structure to make an extended structure, a very beautiful structure that has open space within which nitrate fills the pores to balance the overall positive charge on the linker. They were made as crystals. They were characterized by single crystal X-ray single crystal diffraction. And not only this adiponitrile was reported, but also the shorter version of this linker. Then later, in 1986, the same kind of material was produced by using this diamine quinoline complex. Fundamentally, it's exactly, well, it's the same structure as the one I just showed you based on diamond network, and it's made from neutral linkers again and the copper nitrile linkage. And I will tell you later why it's important to emphasize that these were made from neutral linkages. Similarly, in 1989, Robson reported same kind of structures, again, diamond network made from same kind of neutral linkers and copper nitrile linkage. Then a report from Fujita using metal ion and a bipyridine, another neutral linker and metal bipyridine linkage. And Zawaradko in 1995 reported zinc bipyridine linkages. All these reports, as I'm trying to emphasize here, were involving neutral linkers and linkages made from a metal ion to that neutral linker. So these are bonds that are about 60 to 90 kilojoules per mole. And therefore, the properties of these materials were very different than the properties of the MOFs that I will report today. But the field, when I got to Arizona State University, there were hundreds of these being made, hundreds. And the field was, I would say, in waiting for a major development about what are these things going to be good for. Well, to be able to examine what they might be good for, you have to look at their porosity. And it doesn't take a genius to figure out that when you have these open pores, they're going to be important for catalysis, for ion exchange, for storage of gases. That was already there. For many, many years, people were working on Prussian blues and Hofmann-Clathwaite. They had pores, and people were discussing their use for catalysis, for many other applications. The other thing that became very important is the concept of node, linker, and network. And this originated, and very few people are crediting Wells for this, but this is originated by A.F. Wells. It started in his report in his book, Three-Dimensional Nets on Polyhedra, back in 1977. So what I'm trying to say here is that the idea of building structures from metal organics was there since 1959. And the idea of building structures and describing them by nodes, linkers, and networks is an old idea. So the fact that these structures were all made from neutral linkers meant that they were weak, because those bonds are weak. And so when I got to ASU and tried to exchange the solvents or the ions in the pores, they collapsed, okay? They were not designable because the metals that make up the structure could have many different coordinations. So you couldn't predict whether copper one is trigonal or tetrahedral, so you couldn't predict what structure you're going to make. And definitely they were not chemically stable. They were attacked by solvents like acetonitrile that are also competing for those neutral linkers. So this situation changed completely in 1995 when we showed that the use of anionic or charged linkers increase the bonding strength between the linker and the metal ion. Now these bonds not only take advantage of the lone pair on the oxygen, but also the charge interaction, and they are on the order of 250 to 300 kilojoules per mole, compared to the neutral linker metal ion, which was around 60 to 90 kilojoules per mole. So this was quite a development in that now you can make an open structure in crystalline form. And potentially you can capitalize on that porosity that everybody was trying to do. Well, to prove beyond doubt that a structure is porous, meaning it remains open in the absence of guests, that's called permanent porosity, we needed to demonstrate that these structures could be made architecturally robust. The way we did it, again, is by using these anionic or charged linkers linked by metal ions. And because we were using carboxylate, you can aggregate the metal ions and make what we called SBUs, or secondary building units. These units acted as the nodes, and they were some rigid nodes that made these extended structures, in this case, this square grid structure. Well, to prove their porosity, you have to measure the gas sorption isotherm. This is the only way of proving permanent porosity, short of a crystal structure of the evacuated framework, which we later showed could be done. But in 1998, we reported that the gas adsorption isotherm of this MOF, which had DMF molecules in its pores, once you remove the DMF molecules, you can, as shown here, introduce nitrogen or CO2, and as shown with the open circles, is completely reversible for gas uptake. This is the golden standard for measuring porosity, and proved for the very first time that these structures are permanently porous. And this, while it went unnoticed for a year or so, it became really the beginning of MOF chemistry in terms of proving the porosity of their structures. So strong bonds, these polynuclear building units, or the SBUs, are absolutely essential in building an architecture robust structure. Well, when we reported MOF5, which was made from, instead of a diatomic building unit, now a tetra metallic unit linked together, as you see here, with a charge linker to make an extended primitive cubic structure. This had a surface area of 2,900 meters square per gram, which we reported back in '99. This was really a breakthrough because it broke all records of porosity, and it showed that our idea of the polynuclear SBUs to produce rigid structures that have permanent porosity can be extended to other building units. Well, this SBU approach became really the standard for, and until today, is the way you make MOFs. In that, if I know the conditions under which these clusters form, then I could add the linkers, different linkers with different functionalities, and even linkers that are longer. So in essence, for a solid state chemist, you can functionalize the pores and you can expand the pores. And you can't do that to a solid state materials without breaking it down. But here, it is possible to functionalize the pores and expand the pores without changing the underlying topology or primitive cubic structure of the framework. So in a way, this was a way to design structures, make structures by design. So many other secondary building units have been used in the way I just described. Some of them discrete, as you see here, and some of them are rod-like. And together with Michael O'Keefe, we have basically developed a database that tells this, what structures or what topologies are possible. And so over the last 30 years or so, there's been a lot of activity in the field covering most metals in the periodic table, as you see here, and also a great variety of linkers ranging from very simple, harmless, let's say edible linkers like citric acid or lactic acid, to very elaborate, either very long linkers and elaborate linkers of various topologies and chiralities. So almost anything you can think of could be made into a MOF. And that's the important part, is that now we have a chemistry where imagination is the limit. So whatever linker you can imagine, you can go to the lab and actually likely to make it. So then recently we put together a summary of a lot of the different structures that could result by combining building units. So here you see, let's say, a triangle and a square result in what is called a PTO. This is platinum oxide structure. Okay, this structure could be made from metal organic units where the organic is a square and the inorganic is a triangle, or vice versa, excuse me. You see here that there are many different, in this case, there are two topologies that are based on a triangle and square. Here you have many different topologies. So what I want to say is that for each square, you could spend an entire lifetime exploiting the chemistry of that networks in that space, because you can change the metal ions in your cluster, you can change the geometry of your, the linker, the size of the linker, the size of the cluster, the composition of the linker, the composition of the, so there's almost infinite variations that could be done within that square. So there's extensive chemistry still to be done in this field. Each square here contains the units or the topologies that have been made by combining those shapes. All of these are materials that have been made as MOFs, and continues on with more and more elaborate building units and structures that result from those building units. And you see here there are some squares that are not filled, which for the emerging scholars, such as some of the people in the audience, there are still opportunities to make new discoveries in this field. And especially when you go on to highly symmetric building units, large building units, there's still a lot of space to be developed. And so we have only scratched the surface in this chemistry. But the point I want to make is that if you can think of those building blocks and you can determine their geometry, there is a strategy to determine what structures might result. You can go to the lab and combine those building units and make materials out of that. And because we proved their porosity, now you have a way to make rigid structures that have permanent porosity, and then one is able to exploit the properties of these materials, the porosity properties. So in other words, what I'm saying is that we have uncovered infinite chemistry that is leading to infinite number of materials and infinite number of applications, because we have, and conservatively, I would say, thousands of building units, inorganic building units, thousands of organic units, many, and just as many ways of functionalizing those organic units to make millions of structures. And so far, we've identified hundreds of applications that could be pursued. So this is a great direction, I think, for chemistry. And it has become, since my days at ASU back in 1995, where we published 2 publications. Now the field spans 102 countries, and just in the year 2020, 27 or so publications. So it has become really a worldwide endeavor, and it is, reticular chemistry is now a significant part of chemistry as a whole. It combines organic and inorganic to make new materials, and then these materials are not just beautiful crystal structures, although that's in itself is an amazing thing, but also they are very useful because we were able to prove their permanent porosity, and now we can craft their interior for hydrogen storage, carbon capture, and as I will show shortly, for water harvesting. Before I get to water harvesting, I want to show you that in fact, all this is just the beginning, because what you can do beyond this is you can do things solid state chemists or chemists never were able to do, which is to take many different building units and link them into one structure, okay? Usually, if you take many different building units in chemistry and you try to put them in one structure, you actually get many phases, each containing one or two of those building units. But very rarely can you take so many building units that would come together into one structure. So here's a linker that has been functionalized with many different functionalities, and all can be incorporated into one structure. I'll tell you the significance of that in a second. You can do the same with the metals. You can have structures that are made from 10 different metals, all in one structure. So this multiplicity, which we call multivariate arrangements of functionalities and structure, is bringing on a new thinking in this chemistry. It's introducing a new concept in chemistry, which is, if you think about what you're doing here, let's take just the mop with the different functionalities. Let me separate those functionalities which are covalently bound to the framework. I'll separate them from the framework. And now you can see the framework is periodic, repeating. We know what it is because we have crystal structure of it. And superimposed onto that are the functionalities. We know where they are, but we don't know how they're ordered. Okay, they're disordered. So we don't know their spatial arrangement. But we know that, in fact, the way that they are arranged is very similar in concept to the sequences of nucleotide in DNA. Let me explain this analogy. The backbone of the MOF I just showed you is really very similar to the repetitive backbone of DNA, the polyphosphate sugar backbone of DNA, onto which you have covalently linked nucleotide or functionalities in our case. And you can see that this arrangement introduces new information into the structure. So what I'm trying to say is that the multivariate, our ability to make multivariate functionalities in these structures, takes a structure that is very repetitive and turns it into an avalanche of, or a landscape of unique information across the entire crystal structure. Avogadro's number worth of unit cells are no longer repetitive. Only in the backbone are they repetitive, but otherwise they are, they have heterogeneity superimposed onto them. And this heterogeneity, we believe, is not random, as I will show you in a second, but in fact, it's sequences of information that may potentially code for specific operations. So let me just take this example, where we have a MOF with many different metals, okay? And these metals all lie on the same crystallographic site. So it's difficult for us to tell which metal is sitting next to which. So we don't know their spatial arrangement. So we used atomic probe tomography to examine, let's say, a crystal of this kind. And in this technique, basically, you're subjecting the crystal in a directed way to a laser pulse that removes or that cleaves well-defined segments of the structure, and then you detect which metals are coming out. In this way, this is the crystal. that we have used along, let's say, the chain of metals that would be making up the structure. And in this case, let's say as an example, we showed for that structure where you have cobalt and cadmium, you can get the sequences of metals along each one of these chains. These are 100 chains, 200 chains, 300 chains, so on, up to 700 chains. That's all from one crystal. And then you can look at the results. And the results are what many of you would say are random arrangement. We get that. But we also, depending on how we prepare the compounds, we get short duplicates of metals, or we get long duplicates, or we get insertions. So what this is pointing to, although very, I would say, primitive way of characterizing these, we don't have better ways of characterizing them, but what is very clear to us is that when this heterogeneity is superimposed onto an otherwise ordered system, that you could use the heterogeneity as sequences, and hopefully we can arrange those or design those sequences so that they can code for specific properties. So we think that there is an area that is awaiting to be developed, and that's the sequence-dependent properties, sequence-dependent materials. Okay, so those are the materials. That's an overview of what could be done in reticular chemistry. Now I want to show you what it's good for. One of the things that we have been pursuing is water harvesting, or trying to produce clean water. This is an aridity map of the world. So everything that is not yellow is water stressed. And so you see that almost 1/3 of the world population lives in water stressed regions. Okay, meaning that they don't get enough rain, or that significant amount of the underground water has been used, and it's not being replenished. Questions about water purity arises even in the countries that are heavily watered. So that's another issue. And of course, the third issue is that most countries, 160 countries, import their water. So water is absolutely not just essential to life, but also it's a daily preoccupation in terms of national security. So this is what is being done today in some of those regions, desalination. And desalination, while is a very good way to produce clean water, it is at a major cost, not just energy cost, but also the increased salinity of water, the large bodies of water, whether it's the Gulf or the Mediterranean. There are large bodies of water that are becoming more and more salty. And so that's not a sustainable system. The other thing is that as I mentioned, we are depleting the underground water, not just in desert regions, but even in the Midwest of the US, including California. We are depleting the underground water at a higher rate than it is being replenished. Okay, and this is a photo of a dam that supplies Sao Paulo, a majority of Sao Paulo water, and it's drying up. And so the UN predicts that in the year 2050, almost 5 billion people on our planet will be experiencing water stress, like the examples that I just showed you. We think that there is a possible solution, is that we have a resource that is water in the air, that potentially, if you can find a way of harvesting it, you could create a new source of drinking water. And since this water is recyclable, then it is completely sustainable source of water. This is how many liters of water are in the air at any one time. Okay, so there's plenty of water in the air. The idea of harvesting water from air is not new. This is, biology does it. For example, this species of beetle has nanoridges on its back that allows it to nucleate water from fog, and in the end, drips of water for that it uses for hydration. Okay, but that's from fog. Also, fog collecting is known. This is done in many regions of the world. It's not a very efficient way of making water, but you need fog for it. So what I'm trying to say is that at a humidity, when you have a humidity, let's say at greater than 60% relative humidity, there are ways of harvesting that water. It's not very difficult, okay? But those regions that I showed you, the arid regions, the humidity is less than 60% most of the year, less than 50%. In the middle of the desert, in the middle of the day, the humidity could go down to 5% relative humidity. There are no materials that work at these low humidities. So there are devices that you can buy, as I show here, that work on basically the concept of condensing high humidity, just like the dehumidifier in your house to generate water. They're expensive, they're costly in terms of energy, but you can get clean water that way. But they do not work below 60% relative humidity. They do not work in arid regions of the world. And this is just another way of illustrating that those devices do only work in the blue regions you see here and not in the other regions, okay? So why is that? So this is our vision. Our vision is, could we create a material that takes water from air anywhere in the world at any time of the year, okay? I'm gonna show you that we have probably achieved that. Let me show you the difficulty with trapping water from air. Okay, let's say this is a psychrometric chart of the water vapor in air. So grams of water per cubic meter and plotted against temperature. Okay, so these are the lines of what's called relative humidity. This is 10% relative humidity. This is 20%, 30%, 40%, up to 100%. If you're here, you have liquid water, okay? So let's say that I am in a, so here are two colors indicating this, the arid region, which is this pink, and the green is sort of the, let's call it the more watered regions of the world. But let's say that I'm in a city over here. I'm at 20% relative humidity and 30 degrees C. I have very little water in the air, okay? I have only 5 grams of water per cubic meter, okay? So let's imagine I'm gonna use the technology I just showed you, those machines. To actually condense this water, what I need to do is reduce the temperature down to 4 degrees C before I get to 100% humidity or before I can condense the water. Well, nobody's gonna do that. Okay, that costs a lot of energy. So it's not a good way to make water. However, let's imagine that I have a moth, and that moth is porous and designed to pluck out the water from the atmosphere. Now, with my moth, in that volume, I can increase the humidity from 20% up to a higher humidity, so that now to condense water, I only need to reduce the temperature down by a few degrees to make water. And that's the principle by which a moth works. The moth really, what it does, it concentrates the water in its pores. And if that's part of a system, that means you're creating humidity where there is no humidity, okay? So you're turning the desert into, let's say, into a humid region, okay? So these are the materials that are being studied today, aside from moths, that for water harvesting. And you see this in the literature everywhere. There are zeolites, there are polymers and hydrogels and also molecular structures, and there are inorganic salts. And there are 3 parameters that you absolutely need to have your material be able to do to be viable ultimately as a water harvesting material? One is that your material needs to have high capacity. If it doesn't have high capacity, then you have to cycle a lot. And if you cycle a lot, you need energy, more energy. You also need fast kinetics. If the water goes into the pores and it's stuck in the pores and you can't get it out, or you have to, you can get it out, but it's very slow, then you're not gonna get enough water out. So you need fast kinetics, and you need this material to be able to operate below 50% relative humidity, or in those regions, as I showed you, of where you have few grams of water per in the atmosphere per cubic meter. So zeolites, they're very good, as you know. Desiccants are made, many of them, of zeolites. They love water, so they do take up water from low humidity, but they hold onto the water so tightly that you don't get fast kinetics, and they also suffer from lower capacity for water. Polymers and hydrogels and these molecular crystals, they're great at attracting water. They're very nice at hygroscopic, but they don't have good kinetics, and they do not take up water from low humidity. They only work in humid regions. Salts, they're great at taking water from low humidity, as you know, hygroscopic salts, but they don't have high capacity. And again, you have strong interaction between the water and the salt, and therefore not easy to have fast kinetics. So MOFs, what I'm trying to say is that MOFs solve this problem because they have organic and inorganic components. You can modulate how tightly the water is bound. We discovered, actually quite by accident, because we were studying carbon dioxide capture in MOFs. And part of that, you have to separate the carbon dioxide from water. So we were looking at also water interaction with the framework, and discovered that in this MOF, this is called MOF 801. MOF 801, which is a zirconium MOF linked by simple organic linker, and it takes up water, let's say in at room temperature in the red here, and you see that it takes it up at very low humidity. This humidity is around 20% relative humidity, and it gives up the water in green at relatively low temperature, 45 degrees C. 42% of the structure by weight can be filled with water. This isotherm is beautiful because it shows that a certain amount of water goes in, but then other water follows in a cooperative fashion. And so you get this sharp isotherm, and the water can be taken out. And so your working capacity is maximized because of this sharp knee. Now, when I look at this isotherm, immediately the idea that potentially I could take this MOF to the desert, and at night I can take the water from the atmosphere, and during the day when it's hot, I can release that water. So if I have a container where the MOF is, then I can condense water. So this we discovered in 2014. And this MOF, it's made from, this is the same, let's see, this is MOF 801 made from the zirconium clusters and fumaric acid. We did the uptake and release of water from it, in this case over many cycles, like 80 cycles, without loss of capacity. So the MOF is very stable in water. You can do many cycles without any hysteresis. We saw after the first cycle, there's a slight drop in performance. And so we went in using X-ray single crystal diffraction to see where the first water molecules reside in the structure, and found something quite amazing in that water, the first water molecules make an arrangement, a tetrahedral arrangement. They bind to the metal oxide units, and they make a tetrahedral arrangement that acts like a seed that brings other water molecules in. These are tightly bound, but then the next water molecules are not are only bound to these water molecules and not the framework. This is another pore that makes cubic seeds. And depending on how much water you use, you can have the tetrahedral seeds or these cubic seeds. Beyond these seeds, the new water molecules come in and they bind to these waters and not the framework. And so what I'm trying to say is that the reason we have this nice isotherm, sharp isotherm, is that seeds of water go in, or water molecules go in, they bind strongly to the metal oxide units, onto which you have water molecules that are then attracted from the atmosphere, and that's how the structure builds up. Let's say ice in its pores, or crystal structure of water in its pores. So we use this knowledge to be able to design a sort of a small prototype to show that in fact the MOF works outside the laboratory. So this is a device, almost handheld device. The MOF is put on a surface, and basically what you're doing here is that this is almost like a jar, and you have the MOF in the jar, and at night you open it. Water from the atmosphere goes into the MOF. During the day you close it, expose it to the sunlight. The interior heats up, and as it heats up, as you can see here, the temperature of the interior is 50 degrees C, goes up to 66 degrees. And you can see as it heats up, the water droplets appear and they increase in size. In this experiment, we only use 2 grams of MOF. So 2 grams of MOF didn't produce a whole lot of water, but certainly the experiment worked. The experiment in the sense that you can take this MOF outside the laboratory and show that in fact in low humidity, in this case, the humidity is 30% relative humidity. It does work. Okay, so we then designed a larger system, a 1 kilogram system based on that MOF 801. And our new design is a box within a box. This box contains the MOF, and the outside box, you can think of it as a condenser. At night, air comes in, and during the day, you close the outside box, the inside heats up, and because the walls are cooler, and you get condensation. Okay, and then you can collect the water. This is what the box looks like. It's a simple plastic plexiglass device, nothing more than that. It's cheap and simple. It produces drinking water. For each kilogram of MOF, we were able to harvest 200 to 300 milliliters of water. So as much as, let's say, a cup of water. Just from 1 kilogram, one cycle, taking up the water at night and during the day, releasing it with no energy input aside from sunlight. And the water is pure, and I hope this video shows the student voluntarily drank the water.
1, 2, 3, action. Cheers. Nice.
Well, it's probably not as nice as Eugene likes to admit because it's distilled water. We tested the water for metals, organics, any kind of contamination, and it meets the EPA standards. There are no metals, no organics. It's just pure water. To actually be able to drink this water, ultimately, if you want a drinking water, you just have to add mineralized minerals, which is done routinely. It's very cheap to add the minerals so that it's nice, mineralized water, nice taste. Okay, so based on that, we can now, this is the nice thing about reticular chemistry, in that structure was zirconium MOF, and zirconium is expensive. So we want to make a structure that is based on aluminum because aluminum is cheap. So we chose these aluminum rods, link them with this organic linker to make this structure. I won't describe it, but it's based on rod rods of aluminum oxide linked by organic to make one-dimensional channels. It turns out that in the laboratory, this MOF takes up 0.33 liters of water or 330 milliliters of water per kilo of MOF at low humidity levels. You can see MOF 303 comparison with other materials. MOF 303 is here in blue. It takes up at very low humidity and it has a very high capacity. As I said, the zeolites and the other materials do not do well in terms of kinetics or in terms of capacity. The nice thing also about the MOF is that not only does it take up water at low humidity, but also it releases the water much more easily than any other material. This is the purple line, as you can see here. Within minutes, the water can be released from in that experiment. So we designed another prototype for this MOF 303. This was a little bit more sophisticated. It had cartridges of MOFs where certain cartridges would take up the air while the other ones are releasing the air. We also interfaced the system with a solar panel so that we can do more than one cycle. And we took this MOF, 1 kilogram of this MOF to the desert, to the Mojave Desert, and showed that in fact, I wanted to focus on this humidity level in the desert during the night, very low, during the day, relatively high. And both during the night, during the day, you can harvest water, okay? Ignore this one because that's the water in the MOF leaving Berkeley, where it's a little bit more humid. So once the system is going, you can see that it's harvesting water at night and during the day. Even at humidities as low as 7% relative humidity. And that's really the advantage of these MOFs. This is a real-time picture of water being harvested using that device. You see here drops of water being collected. Okay, so using this MOF, we can harvest 1 liter of water per kilogram. Okay, and now you're talking about significant amounts of water, and because of the release time is minutes, you can do many cycles, okay? Not only can you take it up easily, but also it can be released very easily. And that's the key here, is that with heating 60 degrees C, 85 degrees C, you can get the water out in very few minutes, and that means that with a solar panel to supply electric to run the power to run enough power to run a small fan to push air into the MOF, I can do many cycles, uptake and release. And so based on that, we have designed a system that can do now 200, 250 cycles per day. And this is shown here. I don't know if this movie will work, but let me try to play it. This is the water harvesting chamber up here. And water is collected. You'll see here water condensation, and water will be collecting at the bottom of the device. And this rotation is rotating the exposure of the MOF to the air, where you have modules that are taking up water and other modules that are releasing water. And here you can see the water filling up this bottle. Okay, so the amazing thing here in this device is that we're only using 100 grams of MOF, only 100 grams of MOF. We're doing around 200 cycles, and we are harvesting around 5 liters per day. So 100 grams of MOF, 5 liters per day. That's basically a tabletop, not this particular one, but you can, the next generation device will be a nice tabletop device that delivers around 5 liters per day based on 100 grams of water. And so in terms of capacity, we've gone from very tiny amounts of water per day to 100 liters per kilo of MOF per day. That's real water that now you can think about using it for drinking, for agriculture, to water parts of the world where there is less water, or parts of the world where there is water, but it's not clean water. The MOF, the amazing thing about the MOF, because it works at very low humidity, like 7% relative humidity, it will work in every part of the world. Just the question is how much water you will get based on which area of the world you are. So even in the most driest deserts in the world, the worst you get is about 5 liters per kilo per day. But in general, in most of the desert regions of the world, you're getting pretty high amounts, 40 liters, 50 liters, 60 liters per day per kilogram of MOF. The other thing to keep in mind is that the MOF is regenerated and does not need to be replaced. So you can do many cycles on the same MOF, and the MOF is graded to be in the machine for the lifetime of the machine, which is around 6 years. This MOF is very stable in water, and so far it's been tested over 50,000 cycles in the desert. So with absolutely no impact on the MOF. So we think that we're really changing the water equation in the world. We're showing that these MOFs can be made to be stable in water, and that they can trap water from low humidity, concentrated, and deliver clean water. All right, so I think I'm coming probably down to the end of my lecture, but I just want to say that that's only the beginning, like everything else. There's a lot out there, and the COFs, turns out these covalent organic frameworks could also be designed to make the next generation water harvesting materials. And I just want to show you our discovery here that this COF can take up water from 30% relative humidity, and it's extremely stable. COFs do not have metals. Their backbone is made from covalent bonds. So we think that we are now in a position to develop the next generation materials that are based on COFs as water harvesting materials. So I like to always share this slide, is that if we serve each person in our world 50 liters of water, we would still only have used 0.002% of the water in the atmosphere. So there's plenty of water in the atmosphere. On a fundamental level, what we're doing is not just exciting chemistry, but also we are making water independent of the grid. And we are giving the individual, empowering them to have their own water. And if you don't like your water distilled, you can mineralize it, or if you like it mixed with other flavors, you can also do that. So it's personalized, it's pure water, and our aim is to give citizens of the world water independence. Okay, this is a result of new chemistry that I call reticular chemistry, and it's the control of the strong bond. And just so some of you who are in supramolecular chemistry, just in contrast, supramolecular chemistry is the control of the weak bonds. So finally, in addition to my students and colleagues that I've acknowledged during my talk, I'd like to acknowledge my current group members and these collaborators and funding partners. And I want to thank you, especially the students, for the invitation. I'm happy to answer any questions.
Thank you so much, Omar. That was an incredibly interesting talk. Not only are the MOFs fascinating materials, but you're solving a really important global challenge. We can now have some questions from the audience. If you'd like to put your hand up or to post them in the chat, we can go ahead. We have a hand up from Phil McGuire. Would you like to unmute? perhaps they're away from camera for a minute. What about Mark Wainwright? Did you have a question?
Yes, thank you. Thank you very much. This was a really inspiring and fascinating talk. I have an elementary question from a non-chemist, I'm afraid. I have kind of A-level chemistry and physics from many years ago, and otherwise I'm interested. Just a misunderstanding of mine. So you showed in an earlier slide how using traditional methods you needed to cool the water to a particular temperature in order to extract it, which is why I was then surprised when you were collecting the water at night and releasing it at day when it's warmer instead of the other way around. I understand that there's more water in the atmosphere at night, the humidity is greater, but why is it easier to release it when it's warmer rather than cooler?
Well, you need to release it because water is held into the pores by hydrogen bonds. So you need heat to release the water. But the idea that you trap it during the night and release it during the day, just because you have a little bit more water in the atmosphere at night, and so you can harvest more water. But yes, you can harvest your water in the morning and in midday when it's hotter, you can release it if you like. But it's much more efficient, let's say, for that device, for the passive device. I'm sorry, we're talking about the device that only works on sunlight, no electric, no input of power. For that device, the most efficient way, of course, is at night when you have slightly higher humidity. It's still low, you know, it's not 60%, 80%, still low. You can still collect it and release it if you are off the grid, completely off the electric grid. But once you have electrified device using a solar panel, you can harvest and release 24 hours a day. It's just your productivity at night will be higher. In the midday when it's really low, the humidity is really low, it'll be lower. But if you're running 24 hours a day, you don't need to run it in those times of day where the humidity is extremely low and requires you to, input more energy. So that's the sort of the thing you have to work out in the end for the commercialized version, is that you have to program it so that if you want energy efficiency, so that it's working hard when there's a lot of water in the air at night and slightly less during the day. But in principle, you can harvest water 24 hours a day. Yeah. Yeah.
Phil, would you like to go next?
Hi, sorry, I'm not Phil, I'm Caroline.
Sorry.
On someone else's account, but no, you didn't know that. My question is, you can use this technology to harvest, water from the humidity in the desert. How hard would it be to adapt the technology to purify dirty water?
So there is a lot of work on using MOFs and polymers and zeolites for trapping, let's say, organics from water or harmful ions like cadmium, mercury from water, and there's a lot of research being done on that for cleaning water. So it just depends on what you're trying to take out of the water. I think MOFs do very well because you can functionalize the pores, let's say, with specific metal binding sites that are specific, let's say, for mercury or cadmium. But yeah, so the answer to your question is that yes, they are being pursued for cleaning water. But that challenge is really different than the water harvesting challenge. That's really easier to do than trying to take water where it's present in very small amount from large bodies of air. Yeah.
Thanks.
Yeah, you're welcome.
Thank you. Sally Price has a question in the chat asking whether the MOFs can be poisoned by impurities in the air, and would this lead to impure water being produced?
Okay, good question. We thought about this a lot, and then when we ran all these experiments, even some of those cycles that I was describing where were run when we had those big fires in California. Okay, but in reality, what we have obtained is pure water. And so when you think about it, you realize the MOF itself is a filter, because the pores are not so large as to allow large molecules to go in. So let's say, if you're near a gas station, octane is not going to go into your MOF. Okay, it's going to be kept outside. If CO2 goes into the MOF, since water binds stronger than CO2, CO2 will be kicked out. So small molecules will be kicked out like CO2, but large molecules cannot go in. So we have not seen any contamination in the water, and we have not even filtered the air. So we think that this is operating very nicely because the MOF itself is a filter, since the pore size is not much larger than water itself.
That's great. Andrea asks what the lifetime of the materials is and how many cycles they can do.
So far we test. It takes time, of course, to have long-term testing, right? It takes time because you have to. Your machine is running 24 hours a day. So far we've tested the MOF over 50,000 cycles, and with very little impact on the material. So we're very happy. This is already in sort of, I showed you the prototype, but this is already in commercialization mode. Yeah. So we think that the lifetime of the MOF is the lifetime of the electronics in the machine. And that's usually graded around 6 years. Keep in mind that when the MOF, and if the MOF at the end of the day, at the end of the 6 years fails, you can take it and separate the metal from the organic by adding strong acid and then reassemble it, okay? So MOF 303, the last one I talked about, is made in water. And then when it's not operating after 6 years, let's say, you can disassemble it and reassemble it in water, okay? So there's a zero discharge process.
Thank you. Susan asks whether the MOF structures, if you can predict the properties of them from their structure.
There are a lot of theory groups that are working on this. Chemistry is not very predictable, okay, regardless of what people like to say or do. And I think that that's great. It's great that it's not predictable, because it keeps people like me in business and keeps chemists a necessary part of science. And it keeps us discovering new things. So in terms of predictability, and now I want to answer the question seriously. In terms of predictability, you can, right now, there are ways of predicting isotherm. What correlating structures with isotherms, and then working backwards to give you attributes of a material that would be high performing. So I think that that's based on the isotherm, you can do that. So that's good. In terms of synthesis, for the COFs, they're highly predictable, because and I didn't talk about the COFs, but the COFs, you have organic units that are linked together. You don't make a new entity like in MOFs, where you take the organics and they come together through a metal entity. That sometimes is not predictable. The third component of my answer is that once you make a MOF, the variations you make on that MOF are highly predictable. Okay, because once you know the conditions under which one MOF, let's say MOF 5, can be made, you can always add a new linker with new functionality or a larger linker. As long as you preserve its branchiness or its connectivity, you'll make the same MOF. And so this is a way to design. Okay, so that's just as a follow-up to that question, and I would just want to say that sometimes it's overwhelming going into MOFs to say, well, how do I choose a MOF that's appropriate for a particular application. And if you're not an expert in the field, it's very difficult to do that. So this is one of the overwhelming things that young scholars such as yourselves face when they go in a MOF field. So there's just a dizzying array of structures, and you just don't know which structure to choose for which application. Now, you can narrow down structures based on, let's say for water harvesting, you need a 3-dimensional structure so that you can maximize your pore volume. You don't need a 2D structure. So that you can narrow down the attributes, but at the end of the day, there are a lot of groups trying to answer that question. That's an open question, okay? But the key is that you will find a high-performing material if you, let's say, narrow down and you're willing to do some work. Let's say you narrow it down to a dozen or 2 dozen, you'd be able to get an informed direction. So you can do it empirically. But no, there is not a robust way of correlating a MOF to a property. That is still an outstanding question.
Thank you. Perhaps some of the audience members will be interested in finding them. We have a question from Joe who says, thank you for the great seminar. A non-MOF related question about the active water harvesting device. What kinds of airflow rates do you use? Because they imagine that you need to push many hundreds of liters of air through the MOF to get complete uptake.
Yes, that's a problem that you face with water harvesting, carbon capture from air, is that you have to push a lot of air in. I don't know what the rate is, but we are not using a sophisticated fan. We're using an off-the-shelf fan to do this. So I don't know if that, you probably know the answer if more than I do. I don't know what is the fan capacity, but it's off-the-shelf cheap fan.
Okay. Sophia wonders if the MOF is a filter, could the impurities block the pores over time, and would that reduce the efficiency?
We have not observed blockage of the MOF pores. Remember, the MOF also, we're not using in the last prototype, which potentially is the closer to the commercialization device. You're not using the MOF as a powder. You're actually mixing it with a binding agent to, while still allowing it to be maximally exposed to air. So we have not observed blockage of the pores, okay? You can do this, you can bind the granules together with very little binding agent, but we have not observed blockage of the pores. We do observe a slight reduction in surface area, like 5% reduction in surface area when we bind to the binding agent, but we do not see a degradation of performance because the pores are blocked. Because you just have to think, well, what's in the air? It's probably volatiles. And with all this air moving and water moving in and out, many of these volatiles do not stick to the MOF. Yeah.
That makes sense. Tina says, thank you so much for the fascinating talk. She was wondering if there are possibly thousands of MOFs. How do you choose which of your dozen that you want to investigate further?
Yeah, not easy. I just commented, not so easy. There is just a large number of MOFs. So, I mean, your chemical knowledge can get you to narrow down this vast space into, I would say, maybe 2 dozen candidates, okay? So there isn't an easy answer to that. I think you just have to work in the field and try many different MOFs for that application. You learn the attributes of that MOF that you need for that application, and then things become easier. Okay, either you choose one from that is already reported, or you make your own structure. But there isn't an automated way of correlating. I think this is it would be a great project. I don't think it's straightforward because it's going to require, large computation, long computation time and resources. So, but it's definitely a good project to pursue.
Thank you. Claude, do you have a question?
Yes, I do. Thank you for the beautiful talk, very stimulating. I'm coming to you from Decorah, Iowa, so quite a distance. I'm just, you've explained maybe the general parameters for coming up with an appropriate MOF for this kind of application. I think the MOF that you indicated was the most successful was the aluminum-based MOF. Is that right? Do I have that right? The aluminum?
I think for water harvesting, we went to aluminum because it's cheap.
Okay.
But it was not the obvious choice in the sense that aluminum oxides are very sensitive to water.
Yeah.
But then we found through experience that the metal oxide rods are very stable in water. And then we figured also out where the water was going, and it was passivating the important site in the structure. The very first water molecule that is bound the strongest is passivating the surface, and that's why you can get many cycles without sensitivity to water. So I would say aluminum because it's cheap, but then the rod metal oxide units extremely important because they allow you to have a hindered arrangement of the metal oxygen bonds. And third, the water molecule, the very first water molecule that goes in, passivates the surface and is strongly bound, and it never gets involved in the cycling.
Okay, this is great. You answered the question before I even asked it. That was fantastic. Yeah. And I was going to ask a little bit about the process for coming up with that particular MOF for that application. Thank you very much.
Yeah, you're welcome.
We've had a few questions in the chat on if this was done in deserts on an industrial scale, would there be an environmental impact on air humidity?
I get this question sometimes from atmospheric people with atmospheric science interest. I think that modeling needs to be done. I think some people are I know of some groups that are trying to do that. But remember, this is water that you take out, but then while you're taking out, you're actually replenishing at the same time. Okay, so it's not that you take it out and it disappears. It doesn't disappear. And there are the air is not static. Okay, it's moving, it's changing. So I'm hopeful that we are not. I mean, unless you cover all Southern California with MOP CO3 to harvest water, I don't think we're gonna have a problem. Let's say that's not as urgent of a problem as watering the world. Yeah, okay. But definitely something that needs to be studied. If it becomes more of a wide-scale application.
Alice has a question. She asks, if the first binding water molecules provide nucleation sites for the cooperative binding of further water molecules, could you functionalize the linkers with OH groups?
Very nice question. Yes, I'm sorry. Is that the end of the question?
That's the question, whether that would change the whole structure.
Yeah. You can functionalize a MOF without changing its structure. So you can append covalently a group without, but what I want to point out here is that when you add a functionality, that function is sticking out into the pore, and now your pore volume is compromised or reduced. So for water harvesting, where every drop of water counts, you want to be able to functionalize the pore without introducing atoms protruding into the pore. And That's where, again, that's the magic of reticular chemistry, is that I could add, instead of a nitrogen on that linker, I could have an oxygen and change the properties of the material without changing the pore size, the pore volume, or any of the other, keeping all the other great things about the MOF constant. But I can put on oxygen and get different kind of binding that I might want, or shift the uptake from high humidity to lower humidity because I'm making the pores more hydrophilic. This kind of thing you can play. Pinpoint changes to the linker rather than appending linking groups. Now, in other applications, appending the linking groups where the pore volume is not so important is common and it's desirable. But in this particular case, you already have a great MOF. You just wanted to improve it without changing the other parameters. So you can do those pinpoint changes. Good question.
That's great. Joe asks, when you refer to the cooperative effect, is that separate from capillary condensation that you see in larger pore MOFs?
It is. In this case, the pores are microporous. So they're less than 20 angstroms. And the first water molecule goes in, the next water molecules bind to that water. Then ultimately the pore filling is the capillary condensation and saturation, yeah. But I think that before that is taking place, you have the more water you're absorbing, the more comes in, because the more sites that the new water can bind to. Yeah.
Okay.
As indicated by the shape of the isotherm. Yeah. Mm-hmm.
Okay. Sorry to interrupt. Kresho asks if the magic MOFs, are they easily accessible synthetically, or at high temperatures or pressures are they required?
Most MOFs are made under mild conditions. The MOF CO3 is made in water at, I think it's at 100 degrees Celsius. Most MOFs are made around, I would say 60 degrees to 100 to make them in crystalline form. If you're not interested in highly crystalline material, if you're just interested in a powder, pure powder, but not so crystalline, you can make them at room temperature. And for some application, that's just fine. Yeah.
That's great. I have a final question, if that's okay.
Sure.
I was wondering what your favorite MOF is.
Ooh, well, they change. MOF CO3 is definitely a special MOF. Yeah, because I think that it has we have a chance to really solve the water problem with this MOF. And everything about this MOF is unpredictable. Everything, the binding sites, the rod SBUs, everything about it has been unpredictable. And that's really, that speaks to the power of chemistry and keeping an open mind to what nature might reveal to you. You know, we love, as human beings, we love to predict things, we love to control things, but which is fine, but we should always have part of our effort in discovery. And that's how MOF CO3 was made.
Wow.
Oh.
Thank you. Oh, this has been an incredible talk. I want to thank you again from the whole society. We're so grateful to have you come and speak to us.
Thank you. It's a pleasure.
Thank you so much. I have to give a shameless plug for our talk tomorrow by Professor Charlotte Williams from Oxford, who's speaking on sustainable polymers at lunchtime, and our talk on Thursday from Jolanta Berikova speaking about the adhesive properties of spider silk. I wish we could give you a massive round of applause.